Okay, so take me forever to try and get this set up. This is going to be our first video lecture, hopefully of not too many, on a topic that we haven't talked about yet. Your second to last topic, waves. It's a pretty conceptual topic. It's not too difficult. That's why I'm kind of giving it to you over break. So let's get started. First part of this year, we spent talking almost entirely about particles. You imagine particles like little tennis balls, okay? Just objects that can move from place to place, and they can carry energy with it. If I toss the tennis ball, I can give it some energy. It brings that energy to wherever it goes. All right. So we spent the first part of this year learning about particles. The important part that you need to know about particles: they can move from place to place. They carry energy right with them. On the other hand, there's a whole class of stuff that we have not talked about yet. Those are called waves, as hopefully you can get by my introduction. A wave can bring energy from one place to the next without actually transferring any matter. This is really important. Waves do not bring objects from place to place. They bring energy from place to place, but they don't actually take any mass, they don't take any matter and bring it from place to place. Objects that allow the wave to happen may move back and forth, but the wave itself does not make them move significantly from their original spot. They always seem to end up back in their original place. They kind of just move back and forth. It's almost like a vibration back and forth. They don't end up any closer to, I guess, the end point than when they started off. The actual definition of a wave is as follows. It is a vibration that moves through a medium. And medium doesn't mean like in between like hot and cold or big and small. What it means here is a type of matter or material. So it moves through something. Waves are vibrations that move either through some medium or they are vibrations that move through fields. Now when I talk about fields, I'm talking about electric fields, magnetic fields, some sort of vibration of those fields. In other words, the strength of those fields is either increasing or decreasing. And all waves are created by a particle that vibrates, or here's a good word for you, or vibrating, or oscillating, O-S-C-I-L-L-A-T-I-N-G. Oscillating means to move back and forth around an average position. You'll hear me refer to oscillating a lot in this unit. A particle or a wave causes some particles to oscillate. Basically just a repeated back and forth motion. There are two basic types of waves, okay? There's your definition. Some sort of vibration that either moves through a material or through some sort of field. The two types are longitudinal, L-O-N-G-I-T-U-D-I-N-A-L, and the other type is transverse. Okay, those are the two main types of waves. Those are the main two that we're going to talk about. There are other types of waves, but we're not going to spend a ton of time on them. So we're going to talk about longitudinal first, as soon as I go and check and make sure that our video is still running. And it is, good. Okay, so longitudinal waves are waves in which the vibration, this vibration that causes energy to be transferred from one point to another, in a longitudinal wave, the vibration is parallel to the direction of the wave's motion. And I've got, in class, what I usually do is I have a slinky. Okay, slinkies are great for demonstrating waves. And I have a slinky and I show, here's a longitudinal wave, you can see how it's vibrating back and forth. And here's a transverse wave, and you can see how it's vibrating back and forth. I can't do that here, okay? I don't have anyone else in the room to help me with that. So you're going to have to settle for some videos and some pictures. Here is a picture, you can think of this as, imagine this is a tube full of air. These are all little air particles. And what you can see, it is kind of trippy, is you can see that something seems to be moving from left to right in this tube. That is our wave. The wave is transferring energy this way, from left to right, through this tube. And it might look like the particles are generally shifting down to the right, But if you look specifically at just one of them, you see that it's actually just moving back and forth, okay? Same thing here. While the wave itself is moving to the right, all these particles are just shifting back and forth. Any of them that you see, they're just shifting back and forth. This is really weird. It takes a little bit getting used to. So if the wave is moving to the right, I would describe all these particles as also moving kind of to the left and to the right. In other words, they're moving parallel to the direction that the wave is moving. Okay? Moving parallel to the direction of the wave motion. That's what we mean by this. That was a longitudinal wave. Every longitudinal wave, just a couple facts about longitudinal waves before we move on. Every longitudinal wave needs some sort of medium. In other words, it needs to have a material to travel through. Longitudinal waves can't go through empty space. They need something to travel through. In other words, they cannot propagate. That's just a fancy word for move through. They cannot propagate through what is known in physics as a vacuum, empty space. Okay? This is the reason that you cannot hear sound in space. I'm giving it away, but sound is a longitudinal wave. Space, outer space I'm talking about, outside Earth's atmosphere, is a vacuum. There is nothing there. Well, if there's nothing there, that means there's nothing to, I guess, kind of shift back and forth. So sound will actually not work. Nothing in outer space makes a sound. Another name for waves that require a medium, these are all called mechanical waves. Mechanical waves. Okay, there we go. So, I'm going to show you a real quick video of a slinky undergoing longitudinal wave motion before we get to drawing a picture of it. Okay, I'll maximize it. Here's a picture of a slinky. And this is going to go really fast, so make sure you watch. In the slinky, you can see how the compression moves back and forth through that slinky. He only does one because I don't really understand why. But you can see how that compression kind of moved through the slinky. Now the individual coils of the slinky did move back and forth, but the slinky itself didn't, the whole thing didn't shift to the left, didn't shift to the right. Kind of stayed in place. So we're going to draw a picture of a longitudinal wave on a slinky. Slinky undergoing what I'll call, you can call them longitudinal waves. If you want to be more descriptive, you can even call them compression or elongation waves. Actually, it's doing both of those, okay? In some points, the slinky might be compressed. At other points, it might be elongated or stretched out. So, okay, there are different regions or areas on this wave, or on this slinky, that we can classify. Right here, see how the coils are all pressed together? Same as here, same as here, same as here. All of these are examples. Let me do this, okay? All of these are examples of compression. And all the parts that are a little bit more spread out are examples of elongation. Okay, you can see the compression, you can see the elongation in different parts, but the most important thing with something like this is, let's take any little individual coil. Let's take this one, okay, this one right here. The motion of this piece of wire loop, okay, that makes up the slinky, it simply moves back and forth, okay? This piece of the slinky moves back and forth parallel to the wave direction. Okay? Because you can imagine if you had a slinky and you just like I have a slinky here, I just can't really demonstrate it. You have a slinky and you push it like this. Okay? You're sending basically compression waves down the slinky. The wave is moving this way. The individual coils are also moving in a back and forth motion left and right. Okay? So the wave travels this way. Direction that the wave is moving is like that, and the individual coils are moving back and forth. Okay. Another example of a longitudinal wave, the most important one, like I said, sound waves, and actually one specific type of earthquake wave. You learned about that in earth science, P waves and S waves. P waves are longitudinal waves. They kind of compress and stretch out the Earth's surface. So, those are longitudinal waves. Let's talk about transverse waves now. That is our other type. Okay? So, if a... Oh dear. Guess I gotta reload that. There we go. Okay, hide. Frequency up, pause. Okay, so it's a little tough to see, but these blue dashes right here, this is a transverse wave in motion. I got it in slow motion right now. I can put it in real motion or fast motion. Let's do it real time. But you can see that the wave seems to be moving from left to right, once again. And the difference with this is still a type of wave. It's just a transverse wave. I'm going to put it in slow motion. Or actually, I'm going to pause it so that we can get, let's look just at this little, because basically what this is just a little bunch of dashes that are moving. Okay, look just at this one, okay, centered right under, I guess, my cursor. I guess it won't be under my cursor. Centered pretty much under the O and the W in slow motion. There's a little piece of the wave right here, and I want you to watch its motion. Let me put it into slow motion. Okay, I want you to watch what this piece does. It never goes off this line. Even though the wave itself is moving left to right, the individual particle, imagine this was a string. This little piece of string is not moving at all to left or right. It's moving simply up and down. And that's really interesting, okay? That is what the definition of a transverse wave is. Every piece of the field or material that allows the wave to happen simply oscillates perpendicular to the direction of the wave. Okay, so our definition for transverse wave, let me scroll down here. Transverse waves, and this is the wave that you'll see more often, although you should be very familiar with longitudinal waves. The vibration in a transverse wave is perpendicular to the direction of the wave's motion. This is different from a longitudinal wave, okay? Longitudinal wave, although, some transverse waves do propagate through a material, through a medium. They don't have to. Transverse waves can propagate through a vacuum, which is very good because it turns out that light waves are actually transverse waves. And if you want to bring energy from the sun to Earth, well, there's a big vacuum in between, empty space. Thankfully, light waves are transverse waves, so they can move through this vacuum and go from the sun to Earth. So these types of waves, the reason that they can do this, they do not vibrate matter. Light waves don't necessarily have to vibrate matter. They instead vibrate a field. They vibrate through the magnetic and electric fields. And that sounds really complicated, really weird, but I will get to that in a few videos, actually. We'll talk about that later on. Let me give you an example of a transverse wave. You can do this one with a slinky as well. You just take the slinky and you wave it side to side. I'll video this for you real quick. Okay, here we go. Alright. You can see the slinky moving side to side. They're sending wave pulses down the slinky. You can see that even though the coils are moving, the wave moves from this hand to this hand. Okay, then it bounces back actually. So what happens though is the individual pieces, they move perpendicular. They don't actually move back and forth at all. They don't move, they don't move back and forth between hands, and they end up in the same spot that they started. Okay, that's the key thing with a wave. It transmits energy. It does not transmit matter itself. So, this will look kind of like your typical sine wave from math class. Okay, you see one of these, you know that it is a transverse wave. Okay, and if we have a little piece of this slinky here, or a piece of this, yeah, we'll say it's a slinky, I just didn't draw in the coils. As the wave moves, as this wave travels in this direction, this little particle, this little piece of slinky, moves up and down, basically perpendicular to the way the wave is traveling. Okay, that's what it does. That is the definition of a transverse wave. The individual piece of the wave moves up and down, perpendicular to the direction of the wave travel. Wave travels this way, piece moves up and down. Earthquake S waves, a different type of earthquake wave. They are transverse waves. However, the most important transverse waves are electromagnetic waves. Electromagnetic waves, which are otherwise known as light waves. Okay. Radiation from the sun. I'm going to stop there. I'm going to do a series. I don't want to make each individual video too long because then it doesn't upload very well. So let me stop there.